Hi guys, welcome back to part 3. In the last video I talked about scatter plots, and in the one prior to that we introduced bivariate data. Now I want to talk about a numerical assessment of the strength and direction of relationship, and for this we're going to turn to correlation. So our topic in this video is correlation. Okay, and specifically, we're going to be talking about the Pearson's correlation coefficient. This is going to be our measurement that we're going to focus on. Okay, and what the Pearson's correlation coefficient tells us is it measures the strength and direction of relationship. Rather, good place for me to forget to write linear association. I'll use the word association instead of relationship. It's the same idea. But I stress linear association between two numerical variables. So perfect in the case where we have bivariate numerical data. Okay, this will measure the strength and direction of linear association. So this is not designed to pick up any kind of curvature. Okay, although you will get a number if you just plug numbers into the formula. The symbol for it is lowercase r. It is an example of a sample statistic because we calculate it from sample data. R ranges from -1 to +1. Okay, and as you get closer, so let me draw this in a number line. Let me use a different color. Okay, here we'll put -1, and here we'll put +1, and then directly in the middle we'll put 0. Okay, so as you get closer to either of these boundaries, you get stronger relationships. Okay, so the strongest a relationship can be is -1 or +1. Positive r equals +1 would indicate a perfect positive relationship. R equals -1 would indicate a perfect negative relationship. So perfect positive linear association. R equals -1, perfect negative linear association. Okay, this will be the case when you have a scatter plot where all the points fit perfectly on a straight line, and we'll draw examples of these in a second. Okay, a couple more things about R. R equals 0 is also an extreme case. This is saying there's absolutely no relationship between x and y. Let's put it in those terms. Okay. As far as calculating this, we'll actually leave that to a tutorial in Google Sheets or Microsoft Excel. In other words, we'll let software do this calculation. It's a little tedious. We'll focus on interpretation. So important points about R. R is unitless. In other words, if you were comparing, if your two variables rather were age, which is in years, let's say, and height, which is in inches, then R would be unitless. If your variables were in dollars and years of experience. Income and years of experience were your two variables. Again, R wouldn't have a unit, so it would strip away both of the units of the variables. Okay. The correlation, Pearson's correlation coefficient does not care, or let me write, does not matter which variable you call X and which you call Y. The formula would give you the same exact result regardless of which one you plugged in for X and which you plugged in for Y. And so since we're not going to be plugging these in by hand, when you're doing it on a computer, you could test plugging it both ways and see that you get the same result. Okay? Let's scroll down a bit. So R is sensitive to outliers. So if you have an outlier that you noticed on your scatter plot, it's going to greatly affect the value for R. Okay? What else can we say about R? We're going to actually draw a couple plots, but before we get there, let me also indicate something very important that you've heard before. Correlation does not imply you could finish this. I'm sure you've heard this before. Causation. Okay? Correlation does not imply causation. So what does that mean? So this is saying even if you get a very strong correlation, something close to +1 or close to -1, that doesn't mean that one of the variables is causing the other one. Okay, so a good example of this, it's kind of seems silly, but it actually is backed up by data and should actually make this stick. Okay, this concept of correlation does not imply causation, and kind of steer you away from ever trying to say two things cause each other just because you've noticed that they're correlated to each other. So what's the example? So the example of a study that shows this is we've noticed that as hot chocolate consumption increases, so let me just indicate that by this up arrow. So as hot chocolate consumption increases, crime decreases. Okay, so this has been shown in various studies in different forms. This one showed it with hot chocolate. So basically, if we were to plot this scatter plot and we had hot chocolate consumption over here and crime on the y-axis, so that's y, that's x, we would probably get a scatter plot from what I'm telling you here that look like this, right? As hot chocolate increases, crime decreases. So notice this is the flow, right? Now, that's very interesting, and that would definitely make me kind of perk up and say, hey, what's going on here? But it would be very dangerous for me to then say, all right, hot chocolate consumption causes crime to decrease. So in other words, give people more hot chocolate so as to reduce the crime. Okay? There is actually something else that's going on here that we haven't considered, and since we haven't considered, it's often called a lurking variable. A lurking meaning it's hiding back there, either because we didn't consider it or that it's something that we haven't even we were just negligible of. It just didn't occur to us to think about it. Okay, either way, we didn't consider it, so it's lurking behind the scenes, outside of our reach, and it might be what is actually driving both of these guys. Okay, So both of these guys might be connected to something else or some other things, okay, some other variables to be more specific, that is actually causing it. And if you think of it, by crime we mean mostly, most of crime rather, is by volume is petty crime, not the crimes that you hear of on the news every night, but the petty crimes, okay? Although those other crimes are also included in those numbers, most of them are petty crimes. And when are petty crimes usually committed? When people are out and about, when the weather is warmer. So maybe temperature in this case is what's actually lurking behind the scenes outside of our consideration, and it's actually driving both of these guys. So let's think about that. As it gets colder, people drink more hot chocolate, and as it gets colder, less people going out, less opportunity for crime, okay, from both ends of this of the crime. So crime decreases. This could actually be what's causing this relationship to seem like it's a causal relationship. So it's very dangerous for me to say that the hot chocolate consumption causes crime to decrease. This temperature seems like it's a very possible culprit for both of these. All right, so we have to be careful of that. Okay. Now I'm going to take a little bit of a turn here. I want to look at a bunch of scatter plots. I want to connect the scatter plot tutorial lesson to the correlation coefficient lesson, okay, because they are connected. So let me scroll down and show you a bunch of scatter plots as promised. So these are just some generic scatter plots. These are the x-axis and this is the y-axis for all of these, okay? So let's just look at these. These are just 6 textbook scatter plots. So here we have clearly we're told this, but this is clearly positive. This one's clearly positive. This one, there's no kind of flow to this point. So you can argue this way, but I could argue this way. Actually, nothing really meaningful happens to y as I move around on the x-axis. It's kind of just a flat line. And a flat line is indication of there being no relationship between these two. Going down here, we see that there's a negative flow here. Okay, actually this is more close to it. All right, this one as well, a negative flow. Here, this is positive, but it starts out a little negative. But more important here, there's a curved relationship. Okay, and this is an example of something that we would not be considering, but this is what I was telling you before. The curvature should be pretty obvious to you, and you see it is here. Okay, so let's go through these again and talk about the strength. So let's compare this guy to this guy. The first one is definitely stronger than the second. Just look how much more tightly packed these points are compared to these. Just look how much more scattered these are around the line than this guy. Okay? There's no reason to talk about the strength of a null plot, which is no correlation. Here, the negative ones, we see that this one's stronger than this one. And so I would call this one moderate, as we've done over here, and this one's strong. The curvature, we're not going to say too much more about that since we're not interested in that. Okay. As far as shape, linear, curved. Okay, and we're only going to deal with linear relationships. After I see this scatter plot, I'm not too interested to do much more with it. Okay. All right, now let's go through these scatter plots and just take some intuitive guesstimates of what R would be in each of these. So these are just going to be some educated guesses. Okay, and of course we wouldn't try to calculate the correlation coefficient after seeing this scatter plot, because the correlation coefficient picks up linear association, so it shouldn't be used in this 6th case. All right, so coming to this first one, this is a strong positive relationship. So the sign here is going to be positive, right? And the strongest a relationship could be is 1, and that's when all the points are on a perfectly straight line. We don't quite have that yet, but we do have a strong relationship. So I would say positive 0.9. That would be a good guess. 0.85, 0.8, anything like that would have been good. Here, positive, but a little weaker, so maybe something in the neighborhood of 0.6. Here, no relationship, something close to, let me just do the squiggly equal signs, something close to 0. You never will actually get 0 unless you have a perfectly 0 relationship, and that's not going to happen. So anything really close to 0, 0.01, something like this, 0.04 even, right? Or negative 0.04. Both of those are very close to 0. Enough so that this would probably be the plot, give or take. So both of these, both the picture and the correlation coefficient indicate that there's no relationship here. Moving down here, R is negative. It is a negative relationship, so it's going to be negative. Okay. And we have kind of moderate, so if we're going to be kind of consistent with above, so we'll say this is like 0.6, so let's just make it 0.61. I'm not sure where that 0 came from. Okay, what will the correlation coefficient be here? Sign, direction, negative, and it's stronger than this guy. It's about as strong as this first one, maybe a little weaker, but in the opposite direction. So I would say negative 0.85 would be a good guess here. Okay? So all this was an intuitive practice of the relationship between scatter plots and correlation coefficient. Okay? You would first create a scatter plot. Then if it's appropriate, you would calculate a correlation coefficient, and once you have both of those in hand, they would corroborate each other, they would agree with each other, and they would strengthen each other. Okay? And it would give you kind of this feeling that, hey, maybe there's something more to learn about this relationship. Especially if I'm in a case where I have any one of these 4 here. This story for these 4, of course, each of these is arises from a particular data set. But I would say, hey, there's something interesting going on here in all of these cases. I might want to look into them a little further. The story is starting to unfold with the scatter plot and the correlation coefficient. But can I do more? Okay, and now we can finally get to our simple linear regression model. So in the next part, we're going to see what else can we do, what can we actually walk away with from all this, something concrete. Okay, so continue to watch. Till next time, have a great day.